record button now. So in the following weeks, you will learn a number of theories that explain the formation of coordination compound. So how they are formed. So we will begin with valence bond theory, followed by crystal field theory, and finally molecular orbital theory. So there are three different theories that describe the formation of coordination compound. So we already understand that the ligands are bonded to the central atom via the dative covalent bond. Okay, so the ligands donate lone pair of electrons and they form bond between the metal and the ligand. And then here there are three theories that explain the bonding or the formation of coordination compound. So in first lecture or second lecture, we already learned the magnetic properties of compound. So we first identify the number of the electron configuration, and then you determine the number of unpaired electrons, and from there you can tell whether the complex or the compounds are diamagnetic. So diamagnetic means there are no unpaired electrons. Okay, so if we have, so this is d orbital, we have 5. So if all the if like this is a single electron, it's not pair, so that means it is paramagnetic. Okay, so they have large magnetic effect, so this is paramagnetic. In the case of diamagnetic is when all the electrons are paired, so they all exist as pair. So this is diamagnetic. They have small magnetic effect or sometimes can be ignored. So the magnetic properties, I think you have learned this before to calculate the magnetic properties using the formula. So the magnetic properties depend on the number of unpaired or lone pair or lone electrons. So we have electrons. So for example, this is electron. Okay, inside an atom. So the electrons, they can spin. So they can spin this direction, or they can spin anti-clockwise direction. So sometimes, because of the spinning, so they can cancel the spinning, or they will increase the spinning if the direction of spinning is the same. Like this one, the direction is the same. This is anti-clockwise, so they will increase the magnetic field, whereas the top one here, the spins are in opposite direction, so they cancel each other. So in a paramagnetic compound, so again, paramagnetic, those contain unpaired electrons. So the higher the number of unpaired electrons, the greater the magnetic strength. So if we compare between, for example, okay, we have A and B, complex A and complex B. So for example here, okay, so if you compare this, here, A, in complex A, there are 1, 2, 3, 4, 5, 6, 7. There are 7 electrons, but only 3 unpaired electron. Okay, 3 unpaired electron. Whereas for complex B, there are 5 electrons and all electrons are unpaired. So the magnetic properties or the magnetic strength depending on the number of unpaired electrons, not the number of total electrons. Okay, So for magnetic strength, we look at the number of unpaired electrons. So for complex A, even though it contains more electrons, 7 electrons, but it has 3 unpaired electrons only, compared to complex B, where all the electrons are unpaired. So in this case, magnetic strength of B is much stronger compared to A. So magnetic strength look at the number of unpaired electrons. For diamagnetic compounds, all electrons are paired, so the magnetic strength is small and negligible. So this is what we have learned using the formula. So I think you have learned this, to use this formula, and we also have covered this. Okay, so this is how the Gauss balance work. Okay, so we have balance here, and then this is your sample, and we have this magnetic block. So this is actually utara and selatan. So it's actually northern and south. Okay, and this is your sample. So this we have shown before. So the number of electrons, based on the number of electrons, you can calculate the magnetic moment and you get this value. Okay, so far clear about the what about this? Okay, so valence bond theory. So here, the valence bond theory is introduced by Linus Pauling. Okay. So here, the theory states that the donor atom, ligand, so we have ligand, donates a pair of electrons to the empty orbital of metal. So they will share the electrons, and this is called dative or coordinate covalent bond. So for the central metal atom to be bonded, the empty orbital should be oriented to a certain direction in the 3D sphere. So in order for the bonding to occur, they must have right geometry and right orientation. So even though if the metal has empty orbital, but if the orbital is not at the good direction or good orientation, there will be no bond. Okay, so for example, if we have ligand, so this is ligand, and ligand is p orbital. So this is p orbital, and you have okay, so this is p orbital of the ligand, and then we have d orbital. Okay, so here we have p orbital of ligand, and we have d orbital of metal. So first requirement, the orbital of the electron must be empty. The orbital of metal must be empty. So that's why they can accept electron from the ligand. Okay, so that is first requirement, empty. Second requirement, they should be oriented in a right direction. Okay, so if you compare this example, and if we compare with, so if we have p orbital like this, okay, so this is lone pair of electrons, and imagine if the metal is not in the right direction, then there will be no overlapping. So if, for example, the d orbital like this, so there will be no overlapping because the direction is not right. Okay, so here there will be direction head on. Okay, so remember we learned in there will be head on overlapping, contributing to sigma bonding, and also side by side bonding, sideways overlapping, which correspond to pi. bonding. So they must have right orientation in order to form bond. So the formation of the empty orbital can be explained using the hybridization theory, which include the s, p, and d orbital. So I think in your first year, you already learned the hybridization theory. We can have sp2, sp3, sp3d. So we can have different type of hybridization when the orbitals, they overlap and they form new hybrid orbitals. Okay, so there are three facts to support the valence bond theory. First is the facts from magnetic properties, and then the usage of hybridization theory, and finally the relationship with molecular shape. Okay, so this is what you have learned, I think, maybe before. So the hybrid type, we can have different hybrid, sp, sp2, sp3, dsp2, and d2sp3 or sp3 d2. So for linear complex, you will have SP. So here only two. So for example, we have ML. Okay, so this is linear. Okay, so the coordination number is 2 because it's coordinate to 2. So this is linear. And then we can have trigonal where you have 3 ligand. Okay. So previously, you only learned the coordination number and the shape, geometry. So for this particular topic, we will talk about the hybridization. So this hybrid orbital are responsible for the shape and coordination number. So if we say coordination number 2 is linear and the orbitals, the hybrid orbital is sp. Okay, so this is the relation between hybridization, geometry, and the coordination number. Okay, I think probably that's it for today's class. Just some introduction, and then tomorrow we will go into detail about the VBT for the complex, octahedral, square planar, tetrahedral. So these are the common geometry for the complex. Okay, so I think that's it for our class today. Any question? Any question? Okay. Okay, so if there's no more, if there's no question, I think that's it. So I'll see you again tomorrow at 11, and we will continue with hybridization. And valence bond theory correspond to the octahedral, tetrahedral, and square planar. Okay, thank you very much for your attention, and thank you for listening. See you tomorrow.